Now let us look at the second approach to solve the same problem. Now in this case we are going to use the binary search tree, and the main idea behind using the binary search tree is to reduce the time complexity as much as possible. Now let us see that we have this array which is having the elements 2, 1, 4, 0, 4, 4, 4, 3, 4, 6, 4. Now as you can clearly see here, 4 is in majority. Let us just confirm that. We have the index locations as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. And how many times 4 is coming? It is 1, 2, 3, 4, 5 and 6. Oh, I think 4 is in majority. So for this particular case we are going to use the binary search tree to see if it is in majority element or not. But just for confirming purposes, let me add one more 4 here, and we are going to use binary search tree. So take one element here and insert this node in the binary search tree. We are going to maintain two values. Number one is with every node, that is the number that we are going to insert, and second one is the count, that is how many times that particular element is appearing inside the array. Now let us say the first element is 2, so we are going to add 2 and the number is 1 because it is only appearing once till now. The second element is 1. Now because it is a binary search tree, so we have to add this element on the left of the tree, so it is containing 1, 1, where this first one is representing the number and the second one is representing the count, that is how many times this element is appearing inside the array. Let us say the third element is 4, so we are going to add 4 here because it's a binary search tree, therefore 4 will come on the right of this first element, so it is 4, 1 because 1 is the number how many times 4 is appearing. Now the next element is 0, so 0 is less than 2 as well as it is less than 1, so we are going to add 0, 1. The next element is 4, therefore it is going to be on the right hand side of 2, but because 4 has already appeared, so we are just going to increment the count as 2. So the next element is again 4, so we are going to increment the count as 3. The next element is 4, we are going to increment the count as 4, and the next element is 3. So 3 is greater than 2 but less than 4, therefore it will come on the left side of the 4, so it is going to be 3, 1. And the next element is 4, so again we are going to increment the count of 4. Next element is 6, because it is greater than 4, therefore 6 will come here. And the next element is 4, again increment the count of 4, again the next element is 4, therefore we are going to increment the count of 4 as 7. Now how many elements are present inside this array? A total of 12 elements are present inside this array. And what is the count of the maximum element? Now here, as you can see, we can stop at any stage. We don't have to create this entire tree. I mean, just here, if let us say you have n elements, so it is not necessary that you have to traverse all the n elements. If let us say you have traversed at least 3/4 of this array and you found out that a count of any element is greater than n by 2, so you can stop over there and you can clearly say that this element is the majority element. Now here we can see, after traversing the entire array, we can see that 4 is coming at least 7 times, hence it is a majority element, and for this we are going to use this binary search tree. Now try to find out what will be the time complexity while performing this entire solution. We don't have to sort this array. Sorting is not at all required because we just have to create the binary search tree, but for every element we have to add this element onto the binary search tree according to its position. In worst case, for every element you are going to take log n time complexity to add that element inside the binary search tree. Now let us say we reached to this element. To find the exact position of this element, in worst case you have to check out log n time. Hence, if there are total of n elements and for every element on an average you are applying log n time, therefore the time complexity to solve this problem will be n log n. Now this n log n is much better as compared to the previous case. In the previous case we have seen the time complexity was n square, but now the time complexity is n log n. Therefore this solution is better as compared to the previous solution, right? Now can you find any other solution which can be again better than this? Or can you prove that the time complexity used by this particular solution will be less than n log n? If you can, then obviously you can find a solution. Again, I'm reminding you, the main aim of writing this algorithm is to find a solution where we can find the time complexity is order of n, and we also have to minimize the space complexity. Now for this particular case, we know the time complexity. The time complexity will be order of n log n, but what will be the space complexity? So space complexity, because we require an extra space just to build this tree, that is the binary search tree, and in worst case if you have n element, therefore the extra space that we are going to require will be order of n. Hence there's a trade-off between the time complexity and the space complexity. As the space complexity increases, the time complexity decreases, but if the time complexity increases, then the space complexity decreases. There's a very natural phenomenon because that we have seen in the previous cases also. Okay, now let us move on to the next video and try to see if there's any other method by which we can further reduce the time complexity to a much better solution. If we can, obviously that we can assume is a better solution. Okay, now let us move on to the next video.